It gives me an immense warmth and great pleasure to grace all of your presence. I extend a very warm welcome to you all for this national webinar on smart materials and applications, organizing by PG and Research Department of Physics, Gonzaga College of Arts and Science for Women. It is true that a prayer that comes from the heart can move mountains. It increases your faith and brings you close to God. May I invite everyone to invoke the blessings of the Lord Almighty through a prayer song. Spirit of God in the clear and immortal, blowing to break the trees on the hill. Spirit of God in the finger of morning, fill the earth, bringing to birth and blow where you will. Blow, blow, blow till I meet the breath of the Spirit flowing in me. Blow, blow, blow till I meet the breath of the Spirit flowing in me. Down in the meadow, the willows are mourning, sheeping the caution and cannot like still. Spirit of God, creation is groaning, fill the earth, bringing to birth and blow where you will. Blow, blow, blow till I be the breath of the Spirit flowing in me. Blow, blow, blow till I be the breath of the Spirit flowing in me. Thank you, my dear friends. A beautiful smile is the best universal welcome. It can make the day a good day easily. It's my pleasure to invite Dr. R. Dinesh Kumar, Assistant Professor, Department of Physics, to give welcome address. Welcome you, sir.
A happy morning to one and all gathered here. Small cheer and great welcome makes a merry feast. Today, I am extremely indebted to be a part of this victorious gathering. Primarily, I invoke the Almighty for being kind to all of us. As it is rightly said, research is creating new knowledge. Today, the ultimate aim of this noble gathering is to provide knowledge among the thirsty mind. I welcome you all wholeheartedly. Primarily, I am indebted to welcome our college secretary, Reverend Mother C. Noel Rani, FSAG, on this occasion, which is in all the walk of our college towards successful activities. I welcome you, Mother. Then I am grateful to welcome Reverend Dr. E. Glita Sumangali, principal of our college, who always dreams for the welfare of the college and the student community. I welcome you, sister. It's an honor for me to welcome Reverend Dr. A. John Diana, Vice Principal, who stands shoulder to shoulder in all the positive efforts towards academic excellence. I welcome you, sister. He was a Guru Dronacharya who turned Arjuna a name into definition. Yes, today I am here in this place all because of his able guidance, cordial love and care. I am grateful to welcome Professor R. Jayavel, Dean, AC Tech Campus, Anna University, Chennai, my mentor, my guide, and a man of modesty and humbleness. I bow my head and take immeasurable affection to welcome you for this noble gathering, sir. Then I am extremely thankful and privileged to welcome Professor K. Tangaraju, Professor, Department of Physics, National Institute of Technology, NIT, Warangal, Telangana. I welcome you, sir. What not makes me blessed than welcoming him? I welcome Dr. S. Sudhakar, Senior Scientist, Electrochemical Power Source Division, CSIR, Sikri, Karaikudi, to this noble gathering. I welcome you, sir. He is man of letters who dedicates his life for education and research. I welcome Dr. R. Thangappan, Assistant Professor, Department of Energy Science and Technology, Periyar University, Salem, to this victorious gathering. I welcome you, sir. A scholar's pen is more valuable than a warrior's sword. Yes, he is a powerful man who produces always quality research paper for the welfare of the society. I welcome Dr. Muthu Sendil Pandian, research scientist, photovoltaic device laboratory, SSN institution, Kalavakam, Chennai. For this learning platform, I welcome you, sir. Then I am extremely indebted to welcome the coordinator, Mrs. K. Devi, Assistant Professor and Head, Department of Physics. I welcome you, ma'am. Then I am pleased to welcome the organizing secretaries, Dr. S. Cholan and Dr. M. Manivannan. Welcome you, sir. I am happy to welcome Dr. B. Kupulingam, Assistant Professor, Department of Physics, Cambridge Institute of Technology, Bangalore, who is here with us to deliver the valedictory address tomorrow. Welcome, sir. Then I take the great privilege of welcoming all the staffs of the committee to this webinar. Welcome you all. Then I welcome from Gonzaga family. I welcome the head of other departments, assistant professor from various departments, scholars and beloved students. Welcome you all wholeheartedly. The memories we make with our family is everything. Yes, today we are all here as one family. So I am take due happiness to welcome research scholars, professors, academicians, stakeholders, scientists, head of the departments, student experts, each and everyone gathered here around the nation through this virtual platform. A warm welcome I render you to all. Not in any particular order, I welcome each and everyone through this virtual media. Welcome you all wholeheartedly.
Thank you, sir. A successful person finds the right place for himself, but a successful leader finds the right place for others. It's my privilege to invite Reverend Dr. E. Grita Sumangali, FSAG, our principal, to give the presidential address. Welcome you, sister.
Thank you very much for the invitation. Professor C.V. Raman believes that the success can come to you by courageous devotion to the task lying in front of you. Respected Reverend Mother C. Noel Rani, Secretary, Reverend Dr. John Diana, Vice Principal, Dr. Jaivel, Professor, Crystal Growth Center, Anna University, Chennai, Dr. K. Tangaraju, Professor, Department of Physics, National Institute of Technology, Warangal, Telangana, Dr. S. Sudhakar, Senior Scientist, Electrochemical Power Source Division, CSIR, Sikri Karaikudi, Dr. R. Thangappan, Assistant Professor, Department of Energy Science, Periyar University, Salem, Dr. Muthu Sendil Pandian, Research Scientist, Photovoltaic Device Laboratory, SSN Research Center, SSN Institution, Kalavakam, Chennai, Ms. Devi, Head of the Department of Physics of Gonzaga College, Dr. Dinesh Kumar, Organizing President of Physics Association and convener of this event, organizing secretaries, staff members of Physics Department, staff and students participants from our and other colleges, warm greetings to all of you. I take this opportunity to appreciate the convener and faculty members for organizing national webinar inviting eminent researchers of renowned institutions. I also wish to thank Dr. Jayavel, Professor, Crystal Growth Center, Anna University, Chennai, and other resource persons to take our invitation and accept it to inspire our participants with your extensive experience. And really, I was much happy and elated by the presence of Dr. Jayavel, the famous professor of Crystal Growth Center at Anna University, Chennai. The Department of Physics is organizing national webinar on smart materials and application in observation of National Science Day. Professor C.V. Raman is one of the outstanding scientists given to the world. Nobel laureate Sir C.V. Raman explained his Raman efforts on 28 February 1928. To commemorate his achievements, National Science Day is celebrated every year by the Department of Science and Technology, Government of India. This year, National Science Day has been given the theme, Global Science for Global Well-being. India has already assumed a global visibility. Science is important. You may think, what does the science do? We can't get ready and get connected on without science. Science Day emphasizes scientists and their contribution to their society. It is not alone scientific invention, but it is also their consistent effort to contribute to the problem of the society. It makes humans, the world, and even the planet more sustainable in the world of global warming. Science focuses attention on how individuals and scientists use resources and the environment impact, that is, the results such as to be used for the global well-being. The Global Well-being Initiative is a journey of exploration to understand our common human desire for well-being while also exploring cultural manifestation of our universal striving for a good life. India today is a part of global world. The challenges are global, then benchmarks are also global, and the addressal of all the issues of India is also going to be global operation. Challenges like COVID-19 has proved that such global challenges can be faced again by the scientists globally by global cooperation. Now, we, the researcher, scientific community must work together, keeping in view of global situation. India is rich in knowledge and talent and is taking lead in this approach. We organize national webinar, that is, the Department of Physics is organizing the national webinar just to create about responsibility in strengthening our positions globally. This webinar is to just inspire students, youth, research and innovators to become aware of their responsibility, the great man and his invention by contributing to the world of service through each and every one of our contributions and innovation. I wish the science enthusiasts very best enhance your scientific zeal through this webinar. Once again, I wish God's blessings and congratulations to the organizing team and the convener to have a fruitful session. With this thought, I extend my cordial welcome to each and every one of the resource persons and participants to Gonzaga College and to this webinar to have a fruitful session. Once again, God's blessings, all the best to each and every one of you. Thank you very much.
Thank you, sister. An honor is a special award that given to someone, usually because they have done something good or they are greatly respected. At the very outset, I welcome all our eminent speakers and guests from all over the country from different walks of life. They have come here to share their knowledge and vast experience with the student community. Dr. R. Jayavil, Professor, Crystal Growth Center and Dean, AC Tech Campus, Anna University, Chennai. Dr. K. Tangaraju, Professor, Department of Physics, National Institute of Technology, NIT, Warangal, Telangana. Dr. S. Sudhakar, Senior Scientist, Electrochemical Power Source Division, CSIR, CECRI, Karaikudi. Dr. R. Tangappan, Assistant Professor, Department of Energy Science and Technology, Periyar University, Salem. Dr. Muthu Sendil Pandian, Research Scientist, Photovoltaic Device Laboratory, SSN Research Center, SSN Institution, Kalavakkam, Chennai. I feel happy to welcome you all, sir.
Now I cordially invite Dr. R. Jayawal, Professor, Anna University, to give the keynote address. We welcome you, sir.
Okay. Thank you. Good morning to all of you. Esteemed members of the organizing committee of this conference and invited speakers from various institutions and participants. It gives me immense pleasure to be part of this webinar organized by the Gonzaga College of Arts and Science. And I congratulate the organizers for choosing an important topic which is of more relevant for today's sustainability and sustainable development goal. And the materials which is of focus for this webinar is on smart materials and some of the very prominent applications of these materials, especially for societal needs and also for technological evolution. I'm very happy that the college has been organizing this program as a part of National Science Day celebrations, as it was introduced by the principal. And this year, the focus theme is the global science for global well-being. And this insists that we should have a kind of multidisciplinary, collaborative approach to address the societal problems. And as you all know, the three major challenges which the globe is facing today is energy, environment, and healthcare. And the energy sector, needless to say, we have a lot of developments happening. At the same time, we are also having the challenges to meet with the future requirement because of the increase in the population and also the industrialization of the nations. And coming to the environment, again, there are plenty of issues to be addressed, and the materials become one of the backbones for this addressing these problems, especially for environmental remediation and to address the problems like carbon emission and climate change kind of thing. And healthcare, you all know, we have been experiencing for the past 3 years that how important is the healthcare and also the healthcare developments which protect the humanity from both natural as well as in environmental hazardness. So with this background, this webinar being organized in an important topic, and when it comes to the smart materials, we have plenty of materials available for across various themes for very specific applications, whether it is nanomaterials or biomaterials or energy materials with very specific focus, or ceramic materials, high energy materials, high temperature materials. So we have plenty of materials opportunities available, and some of the materials have been already used for a variety of technologies, and some of the materials are still exposed in terms of its functionalities and properties so that it can be useful for various applications. So today we have materials which are developed in the laboratory will have very extreme properties and functionality. For example, we have material which can have almost 25 times harder than high strength steel alloys, and materials which can have the mobility of charge carriers very close to velocity of light, materials which can have the conductivity almost 5 to 6 orders of magnitude higher than the conventional material, the copper material which we use for transmission purposes. And all these materials are possible to produce in the laboratory, and it is only the requirement is to put them for track to meet the application potential. And in this aspect, I am very happy that there are galaxy of speakers from various institutions. They will be focusing on variety of topics. And with the given development in a multidisciplinary approach in materials and material science as a whole, we have new technologies which are also coming up, and these technologies complement the progress of material science. For example, if you take the advanced technologies like artificial intelligence and machine learning, so we have the impact of these technologies in materials world, probably in terms of studying their multifunctional properties. And when we have multifunctional properties, then the potential of the individual materials can be widespread. And so those kind of functionalities and properties can be narrowed down for a very specific requirement by using the technology like artificial intelligence, where the technology is mainly used for decision making. Similarly, if you develop some kind of theoretical ideas, and those ideas can be validated with experimental parameters derived from new materials or smart materials, what we have today. And this kind of validation gives an opportunity to create some new hypotheses. And it is kind of developing a theory, and based on theory, we develop some postulates, and postulates, leads to some concepts, and then concepts are integrated to look into the experimental validation. And that is the long process to go. So there will be always a very big bridge between the theoretical ideas and concepts and then experimental the observations. But the technologies like machine learning, which help us to develop some kind of concepts, hypotheses based on the experimental observations, and which can be correlated to existing theory, or theory can be theoretical concepts can be immediately converted into hypotheses, then which can be validated with experimental observation. This is a kind of flexibility we have now. So therefore, the new technologies also have a major role to play in expanding the materials arena across various domains. And this kind of materials aspects across various disciplines will also give an opportunity for the students to learn across disciplines and subjects. Because when you talk about materials which have the physical properties of material can be very much applied to various technologies like biotechnology or medicinal field, space technology, defense technology, infrastructure as a whole. And these kind of opportunities can be realized by the students even during their undergraduate or postgraduate studies, because these materials will have options in various fields, and the students will have, if the students are exposed to this kind of multidisciplinary ideas, concepts, then there are a lot of scope for them to develop their intellectual capability, and also they can develop their what is called the cross-culture competence using these materials across various domains. So with this, I once again congratulate the organizers, and especially Dr. Dinesh Kumar. He has been, I know, working for this webinar for the past more than 3 months. And this was actually planned when he took some of his students to Anna University and as an educational tour to Kalpakkam and other places. At that time itself, he has planned this webinar, and I wish this webinar great success, and I am sure the deliberations of this webinar will be very much useful for young students and researchers who are interested in taking up their career in materials science area, and also the young students who are in both undergraduate or PG level to get their knowledge expanded in this domain. With this, I once again thank the organizers. Wish you all the very best. Thank you very much. Dr.
Thank you,
Dinesh?
sir.
Yeah.
Now I heartily welcome Ms. R. Gandhimari, Assistant Professor, Department of Physics, to felicitate Dr. R. Jayavil, Professor, Anna University. Welcome you, ma'am.
Good morning, everyone. I'm honored to introduce Dr. R. Jayavil, a highly respected Dean, AC Tech Campus, Anna University, who has accomplished remarkable achievements in material science and nanotechnology. He is having 31 years of research experience in this field. He has over 15 years of administrative experience as Director, Center for Nanoscience and Technology, Director Research, and Director in Charge, Center for International Affairs at Anna University. He has published about 470 research papers in international peer-reviewed journals. Dr. Jayavil is an internationally acclaimed researcher with the H index of 53, I-10 index of 270, and over 10,600 citations. He has been designated as highly cited author by Royal Society of Chemistry, UK. Professor Jayavil has traveled widely to several countries such as USA, UK, Germany, France, Italy, Norway, Sweden, Belgium, Netherlands, Greece, Japan, Australia, New Zealand, Singapore, South Korea, China, Taiwan, Kenya, and Arab Emirates and Saudi Arabia for collaborative research. Professor, he visiting professor at the Research Institute of Electronics, Shizuoka University, Japan in 2007. University of Göttingen, Germany in 2010. Then University of Queensland, Australia in 2012, and University of South Australia in 2016. So far, 43 researchers have obtained their PhD degree under the guidance of Dr. Jayavil, and currently 10 students are working for PhD. He has investigated several research projects worth rupees 12 crore funded by various organizations like DST, SERB, UGC, AICTE, DRDO, CSIR, MHRD, and DAE BRNS. He has done the consultancy services to industries worth rupees 16 lakh. He has edited a book on advanced materials for optoelectronics. Then he is the chief editor of AU International Journal of Science and Technology, Engineering, Architecture and Management, and managing editor of journal Nano, World Scientific Publishers. Professor Jayavil is a recipient of several awards and recognitions, namely Fellow of Tamil Nadu Academy of Sciences since 1997, then Fellow of Society for Advancement of Electrochemical Science and Technology in 1998, Senior Scientist Award in 2021, and then Academy of Sciences Chennai Mid-Career Award 2021 by University Grants Commission, MRSI Medal in 2019 by Materials Research Society of India, Leadership for Academician Program Fellowship in 2019 by Ministry of Education, Government of India, Research Excellence Award in 2019, Anna University Lifetime Achievement Award in 2019 by Indian Spectrophysics Association, Tamil Nadu Scientist Award in 2016, Active Researcher Award, Anna University in 2012, Science and Technology Agency Fellowship, Japan in 2001, Japanese Fellowship for Foreign Expert in 2004, DAAD Sandwich Fellowship Germany in 2000. Dr. Jaival has received Best Presentation Awards at several conferences organized by Material Research Society of India, Indian Spectrophysics Association, Electrochemical Society of India. He has been the member of several academic and professional bodies like Board of Studies, Academic Council, Research Advisory Council, and Governing Council for many institutions. He was a member of UNESCO Chair in Materials and Technologies for Energy Conversion, Saving and Storage. The future belongs to those who believe in the beauty of their dreams. Dr. Jaival, who is a dreamer and has achieved his goals through hard work and determination. Dear participant, get ready to learn from best person and use it as a source of strength and motivation. Now, I invite Professor R. Jaival to take over the session. Welcome you, sir.
Okay. Thank you, ma'am. Thank you for a very exhaustive introduction. And let me just share my slides. Okay. Is my slide visible?
Yes, sir. Visible, sir.
Okay. Right. So once again, I thank the organizers for inviting me for this presentation today. I'll be introducing a new, it is not a new, but it's a relatively a new kind of class of material called two-dimensional composite functional materials, especially for sustainable energy storage applications. And those who are not very familiar with this energy storage system would appreciate that we have been practicing this device, which we call it as a pentar cell or 2-volt battery, which is have been known for many decades or many devices where we use it for household or small devices, but this kind of energy storage devices have now become industrial scale, especially to meet the requirements for large scale energy storage. And this is the one such battery storage system which is integrated with these things. When it comes to the green energy technology, then the energy storage in terms of green technology is now very common, where we integrate this renewable energy sectors like solar, wind, and this can be directly stored in a device, especially for sustainable development. And the energy storage technology also meets the requirement of what is called Sustainable Development Goal number 7 among the 17 SDGs of United Nations to ensure affordable, reliable, and sustainable modern energy to the society. So with this background, let me just start the work. Actually, the India has started the renewable energy development way back in 20 years ago, but because of the various developments, especially in solar, wind, and other renewable energy sector, and the target which was fixed by 2030 has been achieved almost 9 years before the schedule. Okay, so this is because of the the initiatives both by government as well as the private sector to develop the renewable energies through solar, wind, and other hybrid technologies. And today, the main requirement is how to store this energy for sustainable usage. Whenever we harvest energy, and it cannot be used as a dynamic process, and it has to be stored properly. And there are a lot of initiatives, both in terms of renewable energy sector as well as the recently government has initiated what is called the green hydrogen initiative, with a major grant of about 20,000 crore to develop the green hydrogen, because the hydrogen can be produced by many ways. The simplest way of producing hydrogen is water splitting, and the storage of hydrogen and then use it for sustainable usage is the major task and challenge, and which will be addressed by these the efforts of multiple of institutions working on green energy and green hydrogen technology. So, with this background, let me focus something on the materials aspects, because those who are not very familiar with these 2D layered materials and then applications, and I'll just throw some light on the general energy storage systems which are in practice now, and also what are the future requirements like that. And then I would focus a very specific material, which is a material known for the past 25 years, 20 years, which has got a lot of potential for various applications. And also, if time permits, I'll just discuss some of our recent work on graphene, large area graphene papers, which we have fabricated from our laboratory. And then we have also made some functional devices, and then summarize. And this is actually a new class of material, started with the graphene, and the graphene was discovered in 2004. And now the list is expanding in all dimensions, and we have a variety of materials under the transition metal dichalcogenides family, and then tungsten-based sulfides, selenides, molybdenum-based materials like molybdenum selenide, molybdenum sulfide, and then we have the black phosphorus and the DLC, diamond-like carbon, and then we have a general scheme of materials called MCene, and the list is expanding more exponentially, because we have plenty of materials now. The advantage of this material, for example, if you take a bulk material, it will have a structure like this. And if you isolate the individual layers, and that is what it's called 2D layered materials, and this individual layer is of atomic thick. That means atomic dimension is 10 power minus 10 meters. So therefore, this thickness of these layers will be a few angstrom unit, or we call it a sub-nanometer scale. And if you prepare this sub-nanometer scale material, there are a lot of opportunities and applications. And it is not a very easy job to just isolate this one. For example, if you have bulk, then the bulk has to be fragmented or separated in terms of its physical structure, without compromising the quality or, for example, the defects inside the structure kind of thing. So the structural engineering is the major challenge here in terms of phase tuning or the defect engineering. For example, if you have bulk material, the defects like dislocations or imperfections have a very high influence on the functionalities and properties. But when it comes to this kind of single atomic layer thickness, even a small magnitude of defects will have a very large influence on the properties. Then when we have this kind of layer structure stacked together, the interlayer engineering also another important aspect. And we can make a heterostructures of stacking different kinds of layers of different materials, or the same materials with multiple structures. And the interface engineering and also the stability of interface is also very important. When it comes to the properties of this material, these are all multifunctional materials. And for example, hexagonal boron nitride is a very perfect insulator with energy gap of more than 5 electron volt. and materials like MOS2, tungsten selenide, which are all typical semiconductors with energy gap of 1 to 2 electron volt, and materials like chromium oxide, chromium sulfide are half metallic, and graphene is a zero band gap material, which is semi-metal, sometimes it's metallic, and there are some materials which are highly metallic, and some materials will have very extreme conductivity, and these materials are called superconductors. So we have variety of materials under this category, and if you look into the absorption age, capacity of this material, it covers the entire electromagnetic spectrum, starting from UV to visible, NIR, mid-IR, far-IR, terahertz, and even microwave frequency ranges also. Okay, so because of this, it has got a lot of applications, and in communication, digital analog circuits, interconnects can be made using these materials, and it's also useful for memory and sensor applications. When it comes to the flexibility in 2 dimension, and the flexible devices like transparent conductors, flexible touch screens, or wearable touch sensors, these can be fabricated with this. And if you take sensor alone, we have a variety of sensors possible with these materials, like electrochemical sensor, fluorescence sensors, colorimetric sensors, photoelectrochemical, electroluminescence, and field effect sensor, which is very sensitive in terms of its applications. And coming to the electronics, probably as a student of physics, you know that we are practicing now VLSI technology, very large scale integration devices. And then the VLSI is now moving to what is called the ULSI technology, ultra large scale integration devices, where hundreds of thousands of transistors can be integrated in a single chip. And these kind of materials has given the way that we can realize what is called extremely large scale integration devices. That means we can integrate millions and millions of transistors in a single chip. And it doesn't mean that you fabricate 1 million or 2 million transistors individually and try to integrate this in a single chip. That was not possible. But what they do is they just take millions and millions of electrons, and each electron can act as a transistor, and therefore we can realize what is called extremely large scale integration devices. And these kind of devices are called made with single electrons, or single electron devices, or single electron transistors, like that. And if we come to the biomedical area, we have again plenty of applications, starting from diagnostic, therapeutic, biosensing, bioimaging, and it's also useful to some extent for biosafety applications also. And photonics, we have a lot of interesting applications used on this material. So now if we go for a very specific application, and if you integrate these 3-dimensional materials with the 2-dimensional layered structure, it becomes what is called a 2.5D material. Okay, so all these materials, like if you take a single layer graphene or multi-layer graphene like this, and then intercalate with a 3-dimensional bulk nanostructures, and it becomes 2.5D. And we have graphene or transition metal, chalcogenides or hexagonal boron nitride. All these materials can be integrated with the 3-dimensional structures to have this kind of 2.5D, and the application is very wide. Okay, in the energy sectors, or semiconductor devices, or quantum information devices, single photon emission for photonic applications, spintronics, MEMS devices, sensors. There are a lot of applications of these 2D materials, 2.5D materials also. Okay, so this is also another interesting area. There are a lot of people are working on this integration of the bulk, the 3-dimensional nanostructures with the 2-dimensional layers of materials. Okay, so I'll just give one example of this 2D materials, and probably some of you, those who are working in material science, probably know about this material, which is actually the allotropic form of carbon from graphite, and this graphene can be fabricated. And this was discovered by these 2 Russian scientists who are in the University of Manchester in UK in 2004. and they got the Nobel Prize in Physics in 2010. Okay, so this is a typical layered structure with the C-axis orientation, and if you are able to isolate this base layer or individual layer, and this becomes graphene. Okay, and as I said, the thickness of this graphene is of a few angstrom unit, which is already in the sub-nanometer scale. And these are all typically like other allotropic form of carbon like graphite, diamond, fullerenes, carbon nanotubes. This is made up of two-dimensional hexagonal lattice of carbon with the sp2 hybridization. And the advantage is that the carbon-carbon bonding is the strongest known bond in nature. So therefore, these materials will have a very high mechanical strength. And that is what I told you, that this can be almost 25 times harder than high-strength steel alloy, which we use it for construction and application. And recently there was a report that this kind of graphene oxide is having very high antiviral and antibacterial activity, and therefore the coating of graphene oxide on this face mask or PPEs, personal protection equipment, is very essential, especially to protect from COVID-19 kind of situations. And though the laboratory-made graphene was known only for the past 2 decades, since 2004, there was a recent report last year in 2021 that there was a possibility of this graphene formed almost when the universe was born, by 4.5 billion years ago. And NASA's Johnson Space Center and the Carnegie Mellon Institution in Washington, they had some collaborative research to observe this kind of meteorites, where the surface is basically a layered surface made up of this graphitic layer, and then they also proved that these layers are mostly of graphene nature with very ultra small thickness. And actually, this claim was independently verified by another team of researchers from Tokyo Institute of Technology, and they also compliment that the prediction of this formation of the graphene was 4.5 billion years ago, was complemented by this group also. So that means that it all exists in nature, and we are trying to only retrieve the natural resources for technological evolution or technological upgradation of existing technology. Now, the diamond has been known for many centuries, and then the first diamond was unearthed by sometimes in 1850s. But now there is a recent interest in this lab-grown diamond, and this lab-grown diamond research has been given special focus this year. And some of you would have read in the news that IIT Madras has been given a very huge grant of around 240 crore to develop the lab-grown diamond. Okay. In order to explore the optoelectronic and electronic, mechanical, and thermal properties. Though the hardness is not matching with the natural diamond, but it is possible that all other properties can be tailored or tuned to meet with the requirement for advanced technologies. And these kind of materials, though it was unexplored for many decades or many years, has been brought into light, and then a lot of scope for this. And this was possible with very sophisticated technologies to analyze this material, and also to make use of them for advanced technologies. Okay, well, so with this background, let me just, in fact, we have been working on this graphene-based materials on 4 verticals. One is on graphene, FET, field effect transistor sensors. And this is not a simple gas sensor or chemical sensor or biosensor. We use it in regular applications, but these are all kind of special sensors which will have a very high sensitivity of more than 75% sensitivity, and used for high-end applications like DNA hybridization sensing or C-reactive protein sensing, high-energy radiation sensing, and that sensing of ABC, NBCs, nuclear, biological, and chemical weapons. These are all very technological advancement in based on the sensors. And photocatalysis is another area which many of my students, including Dr. Dinesh Kumar, has worked on that, especially for the advantage of these materials having very high surface area of about uh, close to 3,000 meters square per gram. So if you prepare 1 gram of material, and then application, the area available for your application is about 3 square kilometers like that. Then those kind of properties were exposed by many of my students, and then they did a lot of work on this area. And another interesting area which we have which started is that they're using these 2D materials as a replacement for silicon technology. This conventional technology which we use for all solar harvesting is silicon, and the advantage of silicon is that we can have now almost 20 to 22 percentage of conversion efficiency from the solar light. But when it comes to the requirement, for example, if you wanted to harvest 1 kilowatt of energy from a silicon panel, you need 1 square meter area. And countries like us, with India with 1.4 billion population, we cannot afford to have thousands and thousands of acres of these kind of installations when we go for large scale solar installations. So therefore, wherever we find space, whether it's airport or riverbeds or rooftops, we install these solar panels. Okay. But there was a report that if we have this kind of 2D materials like graphene integrated with the quantum dots to make the more stable structures, and theoretically it has been predicted that amount of photoelectrons observed in this kind of 10 square centimeter area of this panel is almost equal to 1 square meter area of silicon panels. So when it comes to the miniaturization, we have 10 times miniaturization possible. Okay. And this is called a cascade solar cell structure based on 2D materials with integrated with zero-dimensional quantum dot structures. So we have been working on this material also, and this is the energy storage area where we extensively use this material for energy storage in terms of large scale, large energy density, very high power density with a device called super capacitors. Okay. So this talk I will be focusing some of the material options for these super capacitors. Okay. Now coming to the energy storage systems, I am sure that you are all very familiar with this. It's called the vehicles, which are we call as e-bikes now, and these are all basically operating with the lithium-ion battery, and the speed as well as the cost of these vehicles depends on the capacity of the battery, okay, power of the battery. And we have started with e-bike. Now we have 3-wheelers, 4-wheelers, even commercial or passenger vehicles are run through these lithium-ion batteries. And the lithium-ion battery was discovered in 1970s, and it was commercialized by Sony Corporation in 1991. And this discovery was recognized with Nobel Prize in Chemistry in 2019. Okay, and if you just take 2019 data, and it was almost 7 billion units of lithium-ion batteries were manufactured across the globe. And the major manufacturing is from Asia Pacific, because China had the largest manufacturing facility, followed by US, Europe, and Middle East, and also South America. But today the production capacity is around 15 to 16 billion lithium-ion batteries. Okay, especially for automotive industries. But when we look into the Indian scenario, the major challenge of the electric vehicle adoption is the price. Okay, because as such we don't have lithium until last month, I would say. We don't have lithium source in India, and most of the lithium was imported. Batteries were imported from China, Europe, and other countries. And if you look into the import cost from 2016, 17, 17, 18, this is 18, 19. 18, 19 was the peak where that a huge amount of import cost to import lithium and batteries. So then the government of India decided to go for encourage the indigenous manufacturing of lithium. And though we don't have lithium, buying lithium source separately and then making the battery was kind of viable technology so that we can reduce the import cost. So they started restricting the import of lithium and batteries from 2018-19 onwards, and it is going down now. And parallelly, the government has also, and this is actually the lithium production capacity all over the world, because as you said, as I said, the Australia is having the maximum amount of lithium resources through mines, followed by Chile and China, and India was having very almost nothing until last month. And last month there was a report that there was a huge source of lithium in Jammu and Kashmir, which is almost equivalent to the total amount of all these countries, which was almost 5.9 million tons of lithium source was identified, and it has to be explored now through mining, and then we'll come to know how pure it was and whether it is global quality, and all these things has to be ascertained now. So because of these limitations, except Australia, China, Chile, and Argentina, and the other countries had a very minimum sources of lithium, and there was no scope for future development. But India was still optimistic that we can have import of lithium separately, and then we can make lithium and batteries to meet the indigenous development requirement. So there was an agreement signed between Central Electrochemical Research Institute, SECRI, and there was a Rasi Solar group of companies in Bangalore, and they wanted to set up a 1,000 crore facility near Krishnagiri, and the border of Karnataka and Tamil Nadu. Actually, this was signed in 2019, but because of the pandemic and other things, it didn't turn up. I mean, take up still there in the development stage. And Indian Oil Corporation had planned to develop the batteries, especially from indigenous metals, in collaboration with the National NALCO, National Aluminium Company, and other things, to especially to power the India's electric vehicle ambition. And ISR was also planning to set up a huge lithium and battery technology for requirement to automobile sector. Then we have a lot of startups now coming up, especially for battery or storage or charging stations and the peripheral devices. There are 100 plus Indian e-vehicle companies. They are starting, and there is a huge requirement for lithium and batteries for these startup companies. So with this scenario, there are also alternative efforts to look into the other material choices, like alternate to lithium ion, whether we can have transition metal oxides or phosphates or polynoids and metal fluorophosphates. And these kind of materials were also having a lot of potential, and different kinds of alloys combined with metallic and metal oxide kind of things. So this is one aspect. There was alternate battery materials were developed, and there was also a development in terms of fluoride ion batteries. And the advantage is fluoride is highly volatile, and then it will be very difficult to handle. But if you have a very protective environment to handle fluoride, and there was a very rich possibility this fluoride ion batteries can be commercialized for electric vehicle requirement. because the advantage is that we can have almost 10 times more energy density than lithium-ion batteries based on these fluoride batteries. And iron-based batteries also coming up now, and then air-based batteries. Air batteries are coming with lithium carbonate and other 2D material-based cathode and anode materials. So these are all parallel efforts taken by different groups to make materials which is alternative to lithium ion, so that indigenous development of these things are happening. And there was also a competition between sodium and sulfur-based batteries, because these batteries also now competent with respect to lithium ion. For example, lithium will rule the application where the price is not a matter, because the lithium is costly. But sodium and sulfur batteries are, if weight is doesn't not a matter, then we can go for sulfur and sodium-based batteries, which is very competitive, very cost-effective. Only thing was that it is very bulk, because the lithium-ion batteries can be very prepared, very handy, very portable. But as of now, sodium and sulfur-based batteries are very bulk. But there are a lot of efforts in miniaturizing these sodium batteries. So in future, there was a rich possibility where these sodium and sulfur-based batteries can also be prepared very tiny device which is portable or compatible with small scale vehicles like e-bikes or two-wheelers or three-wheelers kind of thing. So another issue is like the power requirement, because the e-vehicles, battery charging is the major requirement. As of now, the lithium-ion battery can have maximum around 200 kilometers mileage. Afterwards, then we have to charge the battery. Whereas the requirement, power requirement is very important for charging these batteries. So therefore, the European crisis now, because of the Russian-Ukraine war, there was a huge shortage of power, and the Switzerland was the first country to temporarily ban the e-vehicles, because they don't have power to charging stations. And if they have this charging power, then their domestic requirement has come down. So in order to meet the challenge, they temporarily suspend the electric vehicle in Switzerland. But this is followed by other European countries also, like Germany, France, because they are also having very acute power crisis because of the war between Russia and Ukraine. But the alternate solution is like not only depending on one particular technology or device, and go for multiple options. And that is where the supercapacitors now realized as an important alternative for large scale energy storage. The advantage is that the power density of this supercapacitors are very extreme, and only thing is the energy density was limited, but also there are a lot of scope for improvement, so that the supercapacitor with the energy density on par with the fuel cells or conventional batteries like lithium ion can be achieved without compromising the power density values. So this is the development, and the advantage is that when we have the rechargeable battery, you want it to have very slow charging and discharging. Whereas the supercapacitor have the very instant charging capacity, recharging capacity. The advantage is, for example, if you wanted to use it for mobile charging, you wanted to have a very quick charge, and then discharge should be very slow so that it can be useful for longer hours. Whereas if you go for automobile industries or logistics, where you wanted to have very quick discharge, and discharging has to be done instantly, because otherwise the vehicle cannot be operated beyond certain speed. Okay, so that kind of high-end applications require this kind of fast charging, where so that the supercapacitor can be useful for that. And there are two ways that we can store energy through the supercapacitor. One is the electrostatic storage, which is called a Helmholtz layer, which is called a double layer capacitors. And energy storage, if you do it by electrochemical process through Faraday mechanism, this is called pseudocapacitors. And when it comes to the material choice, we have different kinds of materials like activated carbon, carbon aerosols, carbon nanotubes, fullerenes, and graphene is the latest addition in this. For double layer capacitors, for pseudo capacitors, we have plenty of conducting polymers and different kinds of metal oxides which can be used for pseudo capacitors. And if we have a hybrid system where the energy storage can take place by both electrostatic as well as electrochemical process, there is advantages where we can go for composite materials, both symmetric or asymmetric supercapacitors, and we can also have the battery type supercapacitors where the energy density can be on par with batteries and power density can be maximum, so that the application potential when range can be widened with all requirements. So the basically the supercapacitor was known for the past was 3 decades now. It was started in 1995, that Russia first used the supercapacitor to power the electric cars, and then the charging system was improved in 2004 in China, the Shanghai High Tech Park, which developed the fast charging system, so that there was a lot of attraction for this charging systems. And then commercial vehicle was introduced in 2006, almost more than 15 years now. And supercapacitor high energy vehicles were also introduced in 2009. So now the flexible supercapacitors are possible thanks to the materials like 2D materials, where we have a lot of applications, and rechargeable supercapacitors are now possible. Okay, so charging, discharging can also be done, and then this supercapacitor can be recharged, so that sustainability can be achieved using this kind of things. And it was started with the small scale applications like memory backup or instantaneous power requirement. And now that application is extended to what is called grid storage. And this grid storage systems can be integrated with the renewable energy like solar. So whenever energy is harvested, it can be stored in this grid. And whenever it is required, then it can be used for applications. So other than that, we have high-speed vehicles, and this kind of high-speed trains can be operated with supercapacitors. And if you look into the market share from 2014 to 2020, there are a lot of improvement in terms of its automotive sector. It was increased from less than 20% to now close to 35%. And then hybrid transport is also now coming up, and renewable energy sector and other infrastructures, grid storage. There are a lot of things, and the electronics becomes a major part because of the so large power density and energy density values. So the future requirement is like the supercapacitors for aerospace and defense applications, especially to make the cost cutting effect, because now the defense cost budget is very huge, and they wanted to substantially reduce the defense budget by introducing this kind of new technologies. And this is actually the generation next high speed trains, where it can be operated at 500 to 600 kilometer speed, where the supercapacitor can have a very fast discharge, so that the vehicle can move with very ultra speed. These are some of the very futuristic application of that. When you just look into the holistic development of this technology, it doesn't depend on one particular area, because it depends on the multiple domains. So people across various domains have to develop this for this technology to get to the matured level, starting from materials to electrodes or electrolytes, and charge storage capacity, and then miniaturization of the design of the supercapacitor cells, and the application potential, starting from wearables to smart electronics, memory device, healthcare devices, or biotechnology related devices. These are all the holistic development of this technology, so that future challenges would be addressed using this technology. So when it comes to the process optimization, we have different kinds of optimization process, including the achieving the higher energy density, power density, and also compatibility or miniaturization and hybrid nature. Okay, so these are all some of the important parameters they have to do in terms of the process optimization. Okay, so the materials choice, I'll take another 5 minutes to address, because I just wanted to explore the material options, and because some of the students who are interested and take up this for their research. And as I said, we have two kinds of materials. One is the double layer capacitors, where mostly the carbon based materials like activated carbon, carbon aerosols, carbon nanotubes, or graphene. All these materials can be used with restricted capacitance of around 500 to 600 farad per gram. And the polymers, as I said, we have plenty of conducting polymers. More than 100 different polymers are possible, and there also the specific capacitance is very much restricted. And the metal oxides like tin oxide, zinc oxide, iron oxide, ruthenium oxide, manganese oxide, we have different kinds of binary metal oxides, where the specific capacitance can be reached almost 800 farad per gram. And the combination of this, either polymers with the carbon or metal oxides with carbon, for example, ruthenium oxide as a base material, if we have activated carbon or CNT or carbon black, all these carbon-based materials can be integrated with binary metal oxides, so that the maximum specific capacitance can be achieved using this material. Okay, so there are a lot of scope for this material to be very effective and having very important application in defining the supercapacitors. And apart from this, we have some kind of metal halide perovskites, because these metal halides are very known now for perovskite solar cell success. And those kind of metal halide perovskites can also be used for energy storage. Not only as a supercapacitors, we can use it for batteries and hydrogen storage, as I told you about the green hydrogen initiative. And when it comes to the energy conversion, it has got both applications in photovoltaic, thermoelectric, and catalytic applications. So these are all actually flexible materials where we can prepare in the laboratory, but it needs some kind of sophistication. And you cannot work with metal halides like other inorganic compounds, because of the toxicity, volatileness, and also environmental hazardous things. Okay. So this is actually the process optimization, which I was telling about this. Why graphene has become superior? Because the reason is it has got a very large surface area of 2,600 meters per gram, and have a very high electron mobility at room temperature. The thermal conductivity is also very high, and because of the flexibility, it has got a very high elastic modulus. Okay, so when we use this graphene for supercapacitor performance, the process optimization includes achieving the higher specific capacitance with the improved conductivity, having a very high cyclic stability, so that repeated charge discharge will not deteriorate the material's performance, and mechanical robustness when we make large scale, and then fabrication scalability. Okay, so today we talk about passenger vehicles, and future the high speed trains or defense or space technology needs large scale scaling up process, and there should be a compatibility of these materials for large scale scaling up. So looking into all these requirements, the graphene is the very well matched material, uh, apart from various 2D materials. But nowadays, MOS2 and tungsten selenide, these materials are also now coming up. But when it comes to the synthesis, the flexibility is that graphene can be synthesized by a variety of techniques. where we can prepare single layer graphene by mechanical exfoliation, thermal exfoliation. People also tried liquid exfoliation for the specific applications, microwave assistant growth, solvothermal, hydrothermal, chemical reduction, chemical vapor deposition, electrochemical synthesis. These are all various methods where we can use. So we don't have to depend on one particular technique, or we don't have to depend on an infrastructure for specific requirement. So whatever the facilities available in your laboratory, it is possible that you can make a graphene structure. And the other advantage is that the synthesis method can also be based on the requirement or the application for which we are making the material. For example, if you want to use it for flexible applications or touch screen, the best way would be the CVD, conventional chemical vapor deposition technique. And if you want to use it for FET transistors, then the patterning of CNT surface or graphene, etching the graphene surface is the most appropriate technique. And for supercapacitors and solar cells, mostly we use the chemical reduction process, which is the cost effective as well as a very simple form we can make without any much sophistication. And if you want to go for high-end biomedical applications, you have to go for micro electromechanical exfoliation or chemical vapor deposition. And for the EMI shielding and other high-strength materials, again, chemical reduction process would be the more appropriate. So to start with, anybody can start with the chemical reduction process which is very simple. And we take natural graphite as the source material because natural graphite is available in abundance, and you can mix with very strong acids like HCl, H2SO4, HNO3, any kind of strong acid will do, only to isolate the layered structure. And then once the isolation is done, we can deliberately introduce the oxygen functional group through the oxidizing agent. And then you can just sterilate and filter it and wash it out to make the graphene oxide powder. And this graphene oxide powder can be mixed with the water, and sonication for 1 hour leads to graphene oxide dispersion, is a colloidal solution. And then from the graphene oxide, in order to reduce to graphene, we can use some kind of reducing agent. Here we have used thiourea as the reducing agent. Okay, so when you just mix with this reducing agent, reflects it at 95 degrees Celsius for 12 hours, you get what is called the graphene oxide, reduced graphene oxide. And if you are able to reduce all the oxygen functional groups, then it becomes graphene. But chemical reduction process, there will be always a residual oxygen functional groups present in the matrix. Therefore, we safely call it as reduced graphene oxide. Okay. Once then other method is okay. So once you prepare this reduced graphene oxide, you can just confirm the extent of reduction of the oxygen functional group by FTIR spectroscopy. This is actually for graphene oxide, and this is for reduced graphene oxide. You can just see there are different kinds of oxygen functional group: hydroxyl, carboxyl, epoxyl, and carbonyl groups. And all these groups, if you are able to reduce, then it becomes graphene. And if you have some residual oxygen functional groups, then it is called RGO. And this is actually graphitic structure. And then Raman spectrum can also be used to confirm the formation of the graphitic layer with the G and D band. And if we have a single layer, we get only the graphitic peak here in Raman. And if you have a stacking of multiple layers, obviously you have defects, and then these peaks are also observed. And the stacking also leads to some kind of overtones like 2D, D plus G peaks appear at the higher wave number side. And the reduction also be done by thermal analysis. For example, if you take graphene oxide, it is thermally stable only up to 200 to 210 degrees Celsius with more than 90% weight loss at 210 degrees Celsius. Whereas RGO is highly stable, where the weight loss is only less than 40% even after 800 degrees Celsius. So these are the simple ways where we can confirm the formation of the graphene structures or graphene oxide structure. So other than chemical reduction process, we have solvothermal or hydrothermal synthesis, which needs a small autoclave, or autoclave can be operated at 300 to 350 degrees Celsius, where we can have a very precise control and size and shape of the structure. When we use the high temperature and high pressure, then there is a molecular mixing, and this molecular mixing ensures the stoichiometry and also crystallinity, and not only for 2D materials, and this can be useful for a variety of almost all 4 different forms of nanostructures, starting from zero-dimensional quantum dot to one-dimensional nanotubes, 2-dimensional seeds or plates, and then 3-dimensional bulk nanoparticle can also be prepared by solvothermal synthesis. Okay. So, okay, well, these are all something about the material, and other parts are like, our research work, which may not be of very interest for you, but why we wanted to is we started with the graphene oxide, graphene, and the reduced graphene oxide and graphene oxide, we could achieve the specific capacitance of about 800 farad by gram, but the current was of the order of microampere, because this implies that you can have very high energy density, but because of the current which is at the range of microampere, we cannot get power density. So therefore, so we have tried with the different composites. Okay, these composite structures are. Is it okay? I think somebody has unmuted. Hello. Hello, Dinesh. Dr. Dinesh. Hello. Dr. Dinesh. What is that?
Yes, sir.
Dinesh, yeah,
Yes,
there are some interference. Is it okay?
Yes, sir. It is audible, sir. It's audible, sir.
Okay. Because there are some disturbance. I thought there is something wrong.
No, sir. No, sir. It's audible only, sir. I have muted the sir.
Okay. Okay, I'll take another 5 minutes. I'll complete. Huh?
Okay, sir. Okay, sir. Yes.
Because I don't want to give all these results. I'll just. So this is actually the electrode fabricated with tin oxide, and this is with cobalt oxide. And the cobalt oxide, they could achieve the energy density of about 44 kilowatt watt hour per kg, and with the power densities of around close to 300 watt per kg. Then we tried with ruthenium oxide, where we could get the current density of the order of ampere range. We started with microampere, then milliampere. Now we achieved ampere range, so that the power density and energy density can be maximum. And then we have just made a 2 electrode working supercapacitor with RGO and titanium oxide. And this is actually different morphology. It's actually bismuth vanadate with one-dimensional morphology was integrated with 2D RGO. And this kind of combination has more stability, where the cyclic stability was very good. So we tried thing. Having done with metal oxides, then we also tried with metal sulfides, like cadmium sulfide, zinc sulfide, and lead sulfide kind of thing. And this kind of sulfides has advantage there, where we can make very tiny particles, so that if it can be easily integrated with the 2-dimensional layers. So this is actually a cadmium sulfide integrated with the RGO layer, and this form a perfect composite. And this is actually the Raman, where you can just see the graphene oxide, D and G peaks, and the cadmium sulfide has a strong luminescence. And then if you make a composite, And you have the graphitic peaks here, graphene peaks. In addition to that, you have the first order, second order, third order linear optical phonon modes, which are very significant for this cadmium sulfide. So another interesting observation is that when we have the pure cadmium sulfide, we have a very strong luminescence peak at 564 nanometer. And when you make a composite, then there is a sudden quenching of this luminescence, and it becomes almost flat here without any luminescence peak. And this is very interesting. For example, if I order to use it for switching applications or optical limiting applications, we can use this phenomena. And in fact, there are a lot of like explanations or interpretations about this very strong luminescence quenching, which is associated with the Fermi energy of this cadmium sulfide and RGO, and also the energy gap, the electron affinity at the surface of this 2D layers and very tiny cadmium sulfide particles. So this is actually electrochemical property. Then we also try to make heterostructures of two different 2D layers like MOS2 and RGO. And this is actually the schematic where you have the graphene, molybdenum disulfide, graphene alternate layers, which was also synthesized by hydrothermal process. So these electrodes were also having a very high current density of the order of ampere per gram, so that this can be useful for achieving a higher specific current power density. And the charge retention after the charge discharge cycle is also highly stable. And we try to make three different combinations, taking a two-dimensional layer integrated with one-dimensional carbon nanotube and mixed with the three-dimensional cerium oxide nanoparticles. So this was done by in situ reduction process, and this process also highly advantages in terms of achieving a higher stability with a very high power density and energy density. So we have tried with the different kind of compositions, because here manganese oxide, cobalt oxide mixed with RGO, this kind of combination actually the important thing is that there are different kinds of morphology possible with the cobalt oxide MnO2, and so it will have very high compatibility with the 2D layered materials, so that we can make a very strong electrodes. So like that, we have done something on nickel, and I'll just skip this part. And then recently we have made nickel, cobalt oxide, and RGO composite structures also. And there is another material called the large area graphene sheets I was telling. This is about 10 square centimeter graphene sheets prepared by modified Hammers method with H2SO4 HNO3 sodium nitrate. But instead of chemical reduction process, we use the inert atmosphere annealing process, where we can reduce the oxygen functional group to achieve RGO. And this was done by self-assembly process. You take graphene oxide and then make a slurry powder and then sonigate it to have a dispersion. And this dispersion is poured on a Petri dish, and the Petri dish is pre-coated with silane, so that it was easy to peel off after the formation of this kind of layered structures. And this was systematically done with all the studies. And we also did some molecular simulation studies to fix the what is called the annealing temperature without any impurities. And see, this is at room temperature at 60 degree, where the 400 degree the molecule is very intact. At 500 degree it disintegrates. So the maximum annealing temperature is would be maximum around 400 or 450. With the 500 it collapses. So we did for both argon as well as nitrogen atmosphere, and lower annealing temperature leads to this kind of impurity peaks. And so therefore, once the optimization is done, and this is the FTIR and Raman imaging, and this is actual size. It's almost a 10 square centimeter area, and this is highly flexible, right? You can bend it, or you can twist it, or you can stretch it, and you can also roll it to make a flexible solid-state supercapacitors. So this is actually uh, the the graphene sheets separated with the polymer separators, and then connected with the LED to demonstrate the charging and discharging effect. And this is actually a very tiny device we have made with two different polymer separators of this graphene sheet. One is PVA H3PO4, another PVA Nafion, to make the electrical actuators. This is bimorphic because of the double layer, and this is very tiny, and it has got 360-degree flexibility. Like, okay, so for example, the robotic arms where they took material which is highly flexible, and then the efficiency is good for in all directions. And this is actually the actuator's performance of the tip displacement for both negative as well as positive bias using this two structure. Okay. And we use this boron doped RGO for as a whole transport for perovskite solar cells also. And recently we have started working on the graphitic carbon, which is also the strongest material. And then we made this kind of fibrous material, and then used as an electrode to make this symmetric 2-electrode supercapacitor. And this is the demonstration where LED powered solid state supercapacitors are fabricated. Okay, this is the performance evaluation for this, and this performance is also very good, and the stability is also very high. And like that, we have made different kinds of material, especially looking at the storage capacity in terms of achieving better energy density and power density for practical applications. I think with this, I'll summarize that we have been working on the 2D graphene sheets and graphene metal oxide composite structures, especially to looking into the improvement in terms of electrochemical performance, cyclic stability, energy density, power density, and also the flexibility. And we also made a multi-core structure with the 3-dimensional bulk nanoparticles integrated with the 2D layer structures mixed with the 1-dimensional CNT for better performance. And we have made the graphene bucky paper as a large area graphene sheets with the flexible structure by inert atmosphere annealing. And then we have used this graphene bucky paper to make some functional devices like solid-state supercapacitors, bimorphic actuators, and perovskite solar cell structures. In fact, we have also recently done the ammonia vapor sensing using these 2D layers. So with this, let me acknowledge our collaborators from NIMS Japan, Lokumar Shrestha and Professor Aliga, and Professor Ajay Vinu from University of Newcastle, Australia, and the PhD student who are mostly contributed for this is Sanmugam and Dr. Thangappan, who is also giving a lecture in this webinar from Periyar University, and Dr. Sengotayan and Selvakumar. So I thank our funding from DST Nano Mission Program, SCRB and MHRD STARS program, and also acknowledge our Japanese collaborator for the NIMS Anna University Joint Graduates Program. Thank you very much. Thank you very much, and I'll be happy if you have any questions or clarifications in this.
Thank you, sir.
Yeah.
It's time for asking question. If anyone wants to ask question, you can proceed or type your questions in the chat box.
Just check whether there is any questions in the chat box.
Yeah, excuse me, sir.
Yeah.
So this is Kishore Kumar from SRM University.
Yes.
Actually, I was doing my research on optical sensors, sir. So
Okay.
I'm planning to use some 2D materials for sensing applications.
Okay.
So actually, I was planning to do some biosensors, like monitoring the human health rates or cancer cells or predicting of cancer cells. So
Yeah.
will you suggest to me about some materials, like a 2D materials? As of now, I was planning to work on transition metal dichalcogenides.
Mm-hmm.
Is that suited for the sensor applications,
Yeah, yeah.
or
In
else will
fact,
you suggest them?
graphene can also be used for sensor applications, but the thing was like carbon-based materials. There was still believe that it will have some toxicity. So the best way, in fact, we also done something on MOS2,
Yes, sir.
molybdenum disulfide. So
Yes,
this
sir.
is very good for biosensors. In fact, we have done some work on glucose sensing, and I told you about that. But this graphene sensor, we use it for DNA hybridization sensing.
Yes,
But
sir.
when you come to these kind of bio sensor applications, especially in order to get rid of these toxicity issues, MOS2 would be the best option.
Okay, okay, sir.
Yeah,
Yes, sir. Thank you so much, sir.
thank you.
Dear participants, if you have any queries, means you can ask the question, or you can post the question in the chat box also.
Okay. Okay, Dinesh. Yeah, I think.
Sir, yes, sir. Yeah, yes, sir. Thank you for your wonderful presentation, sir.
Thank you.
Thank you once again.
Thank you. All the best.
Yes, sir. Thank you, sir. Thank you, sir.
And there was a question that can metal oxide perform an EDLC?
Yes, EDLC. Yes,
Yeah, metal oxide can perform EDLC, especially in ruthenium oxide, manganese oxide. But the thing was that power density was very, very low with metal oxides. Okay, because the electrostatic process, EDLC works on based on the electrostatic process, and so therefore the because of the large surface area, 2D material has more advantage than metal oxides. Okay. I think there was a query that can you share this PPT? Probably I can just share the PPT to Dr. Dinesh Kumar, and then you can have it. Okay. Dinesh, I'll send the PDF of this PPT file. Huh?
Okay, sir. Okay, sir.
Okay.
Once I received, I can transfer the PPT to the participants.
Because the file is very huge, so I have to convert it into PDF file, and then I'll send it to you.
Okay, sir. Thank you.
Okay. Okay.
Thank you for your wonderful presentation, sir. It was very useful to all to grow up in our field. Thank you, sir.
Thank you.
We may conclude this first session. If research scholars have any doubt, you can contact the research person. Thank you, sir.
Thank you. Thank you. Thank you.
Let us start the second session. I extend my warm welcome Ms. M. Ilakya, Assistant Professor, Department of Physics, to felicitate Dr. K. Tangaraju, Professor, Department of Physics, National Institute of Technology, NIT, Warangal. Welcome you, ma'am.
Good morning to one and all present here. I am highly honored and feel privileged to have been given the opportunity to introduce the speaker, Dr. K. Tangaraju, Professor, Department of Physics, National Institute of Technology, Warangal. Sir completed his BSc, MSc and MPhil Physics at University of Madras, Chennai. He completed his PhD Physics at Anna University, Chennai. After his PhD, he started working as an project scientist at IIT Kanpur from July 2008 to December 2008. Later, he joined as a postdoctoral researcher at Department of Chemistry, Sohang University, Seoul. He joined as a senior researcher in the year 2009, and then he started working as a research professor from October 2011 to Jan 2012 at the School of Material Science and Engineering, Jeongsong National University, South Korea. He worked as an assistant professor in Department of Physics, Gandhigram Rural University, Dindigul. Now he is working as an professor in Department of Physics, National Institute of Technology, Warangal, Telangana. His area of specialization is optical and electronic properties of organic semiconductor, physics of organic semiconductor devices, fabrication of highly efficient organic LEDs, phosphorescent organic LEDs, white organic LEDs. Sir has received a Senior Research Fellowship Award on April 2007 by Council of Scientific and Industrial Research, and also he received SCRD Fast Track Scheme for Young Scientist Award by Department of Science and Technology, Government of India, New Delhi. Sir has presented papers in 12 international and 8 national conferences. He has published 29 research articles in internationally recognized reputed journals, and also he published 13 papers in international publications. He has contributed and written chapters in books. He has attended many short courses, seminars, and workshops in national level in the year 2004 to 2017. He has organized the workshop and conferences on teaching and learning of fabrication of thin films and optoelectric devices through hands-on experience in the year 2018 to 2020. He has life membership in Indian Association of Physics Teacher, Indian Laser Association, Luminous Society of India, Indian Physics Association, Optical Society of India, Material Research Society of India, Iron Beam Society of India, and Semiconductor Society of India. 2 students are completed their PhD, and currently there are 2 students are doing their PhD under his guidance. We feel very happy to have your presence here, sir. Now I request our distinguished chief guest, Dr. K. Tangaraju, to take over this section and to give his precious input to our dear students. Welcome you, sir.
Thank you, madam. Am I audible?
Yes, sir, it's audible.
Let me share the slides. Is it visible?
Yes, sir, visible, sir.
Thank you. It's my pleasure to give a talk on this organic semiconductors and inorganic hybrid optoelectronic devices in this conference. So, as sir mentioned, the energy is a very important area where a lot of research has to be taken up to meet the demand of the globe. So let me start with this outline. First, I would like to introduce the organic semiconductors, which is used for the optoelectronic devices, such as organic light emitting diodes, organic solar cells, and UV photo detectors. Based on the organic semiconductor materials as well as the organic inorganic hybrid materials. So as you know that the energy storage, harvesting and storage is very important for these. Because the increasing demand of the energy, we need to have the suitable harvesting system, energy harvesting system, and the storing system. So we have a lot of renewable energies such as the solar, hydrothermal, and biomass and wind. So we need to develop the suitable and the efficient devices to harvest the energy as well as to the storing purpose, because The non-renewable energy sources such as the coal, oil, nuclear sources are depleting and getting drained out in the near future. So because of this increasing demand, so to meet out the demand, we need to have the energy storage, harvesting and energy storage devices. So if you look at the usage of the energy, mostly it is used for the lighting purpose as well as the displays. So displays and lighting are the major sources which consumes a lot of energy worldwide. So if you look at the device which is used for the harvesting the solar energy is the solar cell. All these devices are made up of the inorganic based semiconducting materials. So inorganic based semiconducting materials are wide band gap and it is very strong in the stability, I mean mechanically stable, and it is having the higher charge mobility between 10 to the power 3 to 6 centimeters square by voltage second, and it is having less than 10 milli electron volt binding energy. So it can be easily excited and the energy can be released, even at the visible range. So most of the devices just use the p-type and n-type inorganic semiconducting materials. So the inorganic based semiconducting diode will be emitting the light depending on the suitable biasing. And so when we give the suitable biasing, it will give the light emission in the visible region. Okay, so we have this structure to fabricate the displays and the lighting sources, white light. So combination of the different primary colors will give you the white light, and the white light emitting diodes would be used for the white light sources. So the use of inorganic materials are having the disadvantages. You can see that the fabrication of the LEDs, inorganic based LEDs, will require the ultra high clean room facilities, and the processing temperature is very high, around 1000 degrees Celsius. And also it is very, it uses the costly and toxic chemicals, and the fabrication is also very, sophisticated facilities are required to fabricate the devices, and that's why these inorganic based devices are still expensive. And not only that, the chemicals used in the inorganic based devices are mostly arsenide, gallium, cadmium, and gallium trichloride, and other antimony, phosphor, and other semiconducting materials are very toxic and hazardous to the environment. So when it is disposed in the environment, it causes the life-threatening diseases to the humankind. So to overcome this one, a material which is very non-toxic and environment friendly, and it doesn't make any harmful to the human health, is the organic based. So the organic materials are coming up, and they are prototype, and it is commercially still it is expensive, but these kind of organic semiconducting materials or molecules are going to be the future material for the optoelectronic devices and other other sensors and other devices, so including the energy storage devices such as the supercapacitors and other different types of capacitors. So in organic materials give the electroluminescence properties. The light emission is being harvested from the organic materials. When the organic molecules are made thin layers, and the thin layers of different types, kind of for the electron transporting as well as the hole transporting, and for the different for the light emission. So the different types of organic materials are being used as a layers used between the electrodes, and when the suitable bias is being used, and it gives the electroluminescence. So this is the typical structure of the organic light emitting diodes. So you can see that the electrodes, indium tin oxide is an anode material, anode, and the aluminum is a cathode, in which in between you can see that the different types of organic layers are being sandwiched, and this structure will give the light emission. So you can see that the typical energy level diagram of the organic light emitting diodes. So you can see that the hole transporting material and electron transporting materials are being used for the simple light emitting diodes, in which you can see that the alignment of the energy levels. LUMO energy level is nothing but the lowest unoccupied molecular orbit, and the HOMO energy level is nothing but the highest occupied molecular orbit. Anyhow, we will discuss this energy levels in the organic semiconductor part in the coming slides. So when these two layers are being sandwiched between the electrodes, when the suitable bias is applied, and the electrons would be injected into the electron transporting layer, and holes would be injected into the hole transporting layer, and transported in the charges would be transported in the respective transporting layers, and the excitons would be formed at the center of the light emitting layer, and that the decay of the exciton will be giving the light emission, and the light emission would be coming out of the anode, the transparent anode electrode, and that is how the light is emitted by these organic light emitting diodes. So you could have come across this kind of display devices in your day-to-day life. You can see that from small devices to the large gigantic display devices, made by the different companies and commercially available. You can see that the AM OLED is having the organic light emitting diode, active matrix organic light emitting diodes. This is produced by this Samsung company, and it is available in the market, and the display device is expensive. You can see that the LG OLED TV, which is which is launched in 2017, is having more than 8,000 US dollars. So it is very semi-flexible, and it is very gigantic, and the 77-inch display device. So still the organic based display devices are still expensive because of the material is having a lot of disadvantages, such as the temperature, mobility, and other color combination and its lifetime. So though the challenges are to be met out, the organic materials, organic based devices are considered to be the future display devices. So you can see that the organic based LEDs are showing the higher device efficiency, and it is giving the self-luminescence like inorganic based LEDs, and it doesn't require, but whereas in case of LCDs, a backlight system is required, but is similar to the inorganic based LEDs, it is showing the higher device efficiency. So this, because of this reason, it is much, it is giving the much very high efficiency when compared to the inorganic based LEDs. And the fabrication process is very easy when compared to the inorganic based one. So inorganic based high temperature process is required for the inorganic based LEDs, whereas here it can be just used by the spin coating and inkjet printing for the large area coating purpose. And so this made the device very low cost and lightweight, and because in a very thin layer of organic materials are required of the order of nanometer. So around the total thickness of the whole device would be of the around 100 nanometer. So such a thin layer of thin layer based organic layers will make the device very cost effective and affordable. And so the organic molecules are very flexible. It can be deposited on the the very flexible substrates, and hence it can be made roll to roll, manufacturing large area roll to roll devices can be made possible. And it is also giving the higher brightness and the large wide weaving angle of the device is one of the advantages when compared to the inorganic based LEDs. In case of inorganic based LEDs, hardly 160-degree angle would be the weaving angle or less than that. When it comes to the organic based LED, and it gives the weaving angle of the display devices more than 170-degree. And also it is giving the faster response less than 1 microsecond, and hence it can be used for the switching applications. Very importantly, these organic materials or organic molecules are non-toxic, biodegradable, and environment friendly. It can be easily biodegradable, and it can be thrown out, and it will be it will not make any hazard to the environment as well as to the humankind. So these are the advantages. So because of these advantages, the organic material based electronic devices and other sensors are going to be the future devices. So as I already mentioned, the challenges are the operating temperature. So when the device organic molecule based devices are operated at the room temperature, you can see that because of the Joule heating effect, there would be a large amount of heat would be generated at the molecule. So because of this large heat, molecule will get broken, and the conjugation would be damaged, and hence the lifetime of this particular device would be deteriorating as the operating on the continuous operation, the lifetime would be decreased. And also these kind of organic molecules are not periodically arranged. It doesn't make the the charge transportation from one end of the molecule to the another end, and it is just by hopping process. Electrons are jumping from one molecule to another molecule, and that hinders the mobility of the organic molecules and leading to the low charge mobility. And this is low charge mobility is one of the issues to be addressed. And also the organic molecules are very sensitive to the oxygen and water when it exposed to the oxygen and water in the normal ambient. So the device organic molecules will get damaged, degraded, and hence the organic molecules will be degrading very fastly. So to overcome this issue, now the commercial organic devices are being vacuum sealed, and that leads to the very expensive device. And also these thin films, organic thin films, are currently made by the vacuum deposition process, such as the thermal evaporation process and other chemical vapor deposition process, to make the devices. And this should be addressed. And the very importantly, color imbalance. To make the white light source, we need to have the three primary colors: blue, red emitting organic molecules. And because of this wide band gap, the blue emitting organic molecules are having very less lifetime because of this wide band gap. And when we make the when we make these lighting sources, white light source, the blue light emitting organic molecules will get deteriorated very fast than the other organic molecules, and hence the color purity will be gone bad within short time. So in order to maintain the higher lifetime of this white light source, the the wide band gap blue emitting organic molecules should have the higher lifetime. So so the color imbalance and the lifetime of the organic molecule is one of the issues to be addressed. So these are the challenges for the organic organic material based devices to be commercialized for at the affordable cost. So, so I just want to brief about the, before going into these basics of the organic semiconducting molecules, I just want to let you know the typical structure of the organic light emitting diodes for the display applications. If you look at the display, uh, it is nothing but the array of LEDs arranged, arranged in a manner called the technology is called as active matrix technology, where the each LED, small tiny LED would be addressed by this technology called active matrix technology. So here you can see that the arrangement will have the three primary color emitting light emitting diodes. So that each diode will have the typical layers of organic molecules for the hole transporting, electron transporting, and light emitting. So these organic layers, thin layers of thickness around 60 to 100 nanometer would be, or even less, would be sandwiched between the transparent anode and the cathode, aluminum cathode, most widely used silver or aluminum cathodes. So this is the typical structure of the organic light emitting diodes used in the displays. So these are the typical molecules used for the hole transporting as well as the electron transporting and light emitting. So where you can see that this ALQ3 is one of the most widely used electron transporting as well as the light emitting layer in organic light emitting diodes. So the major disadvantage which should be overcome is the free carriers. The free carriers are not available in the organic materials, unlike inorganic based semiconducting materials. So here in case of organic material, the electrodes will inject the carriers, and the carriers would be transported by the respective charge transporting material, and the light emission would be taking place in organic molecules where the excitons would be generated. So let me introduce the organic semiconductors. So organic semiconductors are nothing but the conjugated organic molecules which will have the alternate single and double bonds. So this kind of conjugated organic molecules will exhibit the semiconducting properties, and that will have the the semiconducting charge mobility around close to the inorganic based semiconducting material, close to 10 to the power minus 3 to 10 to the power minus 1 centimeter square per voltage second is the charge mobility achieved for the highest charge mobility achieved for the organic semiconducting material based on the anthracene. So here you can see the typical organic molecules used in the organic light emitting diodes. So they are classified into three categories: small molecules, oligomers, and polymers. Depending on the conjugation length, they are classified into these three categories, and they will be used in the various applications, right from the LEDs and solar cells and photovoltaic cells. And polymers are the very long range conjugate organic structure, which will be most widely used in the solar cells. So you can see that the organic semiconductors will have carbon core structures in which the sp2 hybridized electrons will make the alternate single and double bonds, which will be which will transport the electrons from one end of the molecule to the another end, and that will be the flipping of the loosely bound pz orbital or the p orbital electrons will make this transportage of transporting of charges electrons from one molecule to the another molecule. So so you can see that the hybridized sp2 orbitals will make the bonding in the molecular plane, and that will make the sigma bonding. The sigma bonding will be more stronger than the loosely bound p orbital electrons. So you can see that in benzene molecule, if you look at the benzene molecule, there would be 6 carbon atoms. 6 carbon atoms will bound together via this van der Waals bonding. So in this molecular plane, the sigma bonding would be made. The sigma bonding will be stronger because of this higher degree of axial overlap of the electronic wave functions. So it will have the wide band gap, so in the UV range. So it will form the sigma bonding. Sigma bonding will have the higher in energy, and the sigma star will have the lower in energy. It will make the the electrons in the sigma star bonding will have the very low energy, whereas the electrons in the sigma bonding will have the very high energy, which is around the UV range. So the pz orbital or the p orbital, leftover p orbital, will make the side to side overlapping with the carbon atoms, and that will make the additional bonding called pi bonding. The pi bonding is much weaker than the sigma bonding, and hence this pi bonding will be flipping between the carbon atoms. So because even very small energy is required to flipping of this bonding, side to side overlapping of this p orbital bonding, and that will come to the flipping, and this by means of this flipping of this pi orbital will make this charge transport throughout the molecules. So the pi orbitals will have the energy levels between the sigma bonding and sigma star bonding, and so the transition of the electrons from the pi orbital to the pi star orbital will be lying in the visible range. So the energy in the visible range will give you the transition of electrons from the pi orbital to the pi star orbital. So the energy levels will be filled up in the organic molecules so the energy will be first the electrons will be filled in the sigma bonding and pi bonding, and depending on the energy absorbed by the organic molecules, and the pi orbitals will make the transition, and then sigma star orbital depending on the, if it is the visible light is striking the organic molecules, the electrons in the pi orbital will make the transitions. So if it is in the ultraviolet and more than that, so the electrons in the sigma bonding will make the transition from the sigma to sigma star orbitals. So you can see that the filled in energy levels and the unfilled energy levels, the first or the highest filled orbital is called as a highest occupied molecular orbit, and whereas the lowest unoccupied molecular orbit is called as a LUMO energy levels. So the energy gap between these pi orbital and pi star orbital or HOMO to the LUMO is called as the optical band gap of this particular organic molecule. So this is close to the the valence band of the inorganic semiconductor material, and this is close to the conduction band of the inorganic semiconductor material. So you can, as I already mentioned, you can see that in the organic molecules, the sigma bonding and pi bonding will make a important role to give the charge transport and the electron transition by means of absorption of the external energy. So most of the UV energy will make the transition from the sigma to sigma star orbital, and the visible light will make the transition from the pi to pi star orbital and n to pi star orbital. N is nothing but the non-bonding orbital. Non-bonding orbital would be formed by the lone pair electrons present in the organic molecules, or any other foreign moiety attached to the organic molecule will make the non-bonding because of this lone pair electrons. So that will make the transition in the visible range, and that too in the far visible range in the red regions. So if you look at the benzene molecule, the p orbital electrons will make the flipping from one end to the another end. It will make the transport of the electrons in this benzene molecule. So you can look at this image where the above and below the molecular plane, the electrons would be delocalized because of this flipping of these pi orbitals. So that is pz orbitals. So in the due to this delocalization of the electrons, there would be a band of LUMO or pi star orbital corresponding to the conduction band in the inorganic, and similarly there would be a band of HOMO orbitals. HOMO orbitals will make a band of energy levels corresponding to the valence band of the inorganic semiconductor material. So there would be a band of energy levels corresponding to the valence band. There would be a band of energy levels corresponding to the LUMO band LUMO band will be corresponding to the conduction band of the inorganic base semiconductor material. So when the benzene molecule is taken, and there would be 18 sp2 orbitals will make a sigma bonding and then sigma star bonding, and this will make the UV transition, and the band of a HOMO band and the LUMO band transition will make the visible emission in this organic semiconductor material. Typically, the polymers will make the large number of LUMO and HOMO energy levels, which will make the bands corresponding to this valence band and conduction band of the inorganic semiconductor material, and which will give the energy transitions in the visible range as well as the UV range. So in case of organic semiconducting material, there would be a different types of excitons would be formed. So right from the Frankel very short range excitons and the charge transfer excitons, intermediate or charge transfer excitons, and the long range exciton is called as a van der Moot excitons. So these are the different types of excitons formed in the organic semiconducting material. So the exciton is nothing but the electrostatically interacting electron hole pair. So this will make the electrostatically interacting electron hole pair will be called as excitons. This will be decaying to give the light as well as the non-radiative transitions. So there are different types of transition from the organic molecules. So when there are different states, singlet and triplet states. If the spin of the electron is paired, that is called as a singlet state. If the spin of the electron hole is unpaired, that is called as a triplet states. So you will have an organic molecule singlet and triplets. So when the external energy greater than the band gap of this or the optical band gap of this organic molecule is striking this organic molecule, there would be absorption process will be taking place, and hence the molecule will get excited. So excited molecule will make the excitons. So excitons will be formed in the excited molecules, and the excitons will be decaying in the different process. So from the singlet to singlet, the triplet to singlet will be making. So if the exciton decay is taking place from the singlet to singlet, and the energy difference is emitted as a photon, and that kind of emission process in the organic molecule is called as a fluorescence. Suppose if the transition, the exciton decay is taking place from the triplet to the singlet, and that emission is called as a delayed fluorescence or the phosphorescence. Phosphorescence would be taking place of the order of that time scale, in the time scale of millisecond, whereas the fluorescence will be taking place in nanosecond to the picosecond in organic semiconducting materials. So in addition to these fluorescence and phosphorescent emission from the organic molecules, there would be other kinds of non-radiative transition, so such as the Forster energy transfer and Dexter energy transfer process, by which either the photon would be absorbed by the acceptor molecule, or there would be a transition of the electrons between the donor molecule and the acceptor molecules. So by means of either absorption of the photons or by means of direct exchange of electrons, the donor will transfer the energy, or donor molecule will become the donor molecule will come to the ground state, and the acceptor molecule will go to the excited state to give the energies. So to give the to make the energy transfer from donor molecule to the acceptor molecule. As I already mentioned, the free carriers are not available in the organic molecules. It has to be injected into the organic molecules and also transported not through the throughout the material, but just by hopping of charges from one molecule to the another molecule, which are not randomly arranged in the organic thin films. So in the organic thin film, the randomly arranged organic molecules will make the the separation of this overlapping of electronic wave functions, which will cause the the reduced mobility of the charges. So the hopping process will be taking place to give the mobility in the organic molecules, and these organic molecules would be used for the purpose of light emission as well as the light energy harvesting. So in case of light energy harvesting, there should be a dissociation. The electron and the exciton get dissociated. So in case of for the light harvesting purpose. So in case of when the exciton is getting dissociated, the electron and holes will be separated out, and that will be contributing to give the current. And so the dissociated electrons will contribute the current, and that will be used in the solar cells, whereas the excitons will be decaying to give the light emission. So this phenomena is used in the organic light emitting diodes. So the excitons formed in the organic semiconducting molecule will have the diffusion length. So if the dissociation is taking place within the dissociation length, and that process will be used for the solar cells. If the dissociation, the exciton diffusion length is larger, and within this exciton dissociation length, the exciton is decayed, and that kind of process is used for the light emission in the organic light emitting diodes. So these are the, this is how the organic molecules will get excited and give the light emission along with the other non-radiative process in the light emitting diodes as well as the solar cells. So it has the many advantages. You can see that when compared to inorganic semiconducting materials, organic materials are very weak because the bonding is made by this van der Waals bonding, whereas in inorganic semiconducting materials it is made up of covalent bonding, and that is the reason why the material is mechanically stronger when compared to the organic. And the charge carriers are not confined to the atoms. It is, in case of inorganic, it is free to move throughout the volume of these inorganic materials. Whereas here, it has to just hope it has to be hoped from one molecule to the another molecule, and hence it limits the charge mobility. Whereas you can see that the charge mobility is very high when compared to organic material. So in organic, the charge mobility is just reached to 1 centimeter square by volt second. So and the binding energy is, this is very, very less, whereas here it is still very large, and the device fabrication is very low, and it is very sensitive to the ambient. So and hence because of this sensitive nature, the organic materials are still vacuum sealed in the devices, and it leads to the expensive device cost. So let me discuss about the working of organic light emitting diodes. So you can see that this is the typical energy level of the organic molecules, which will be used for the respective purpose, such as the hole transporting and electron transporting. So you can see that the energy level of the indium tin oxide is an electrode which will be transparent. So the indium tin oxide is a transparent electrode which will be used to extract the light emitted from the light emitting diodes. And here we are using the combination of lithium fluoride and aluminum as a cathode to inject the electrons into the organic material, as well as to reflect the light from this electrode. So when the anode is injecting the holes and the cathode is injecting the electrons, so the respective charges would be transported by the respective material, and there would be a formation of excitons in the light emitting layers. So the excitons would be recombining to give the light emission. The emitted light would be reflected by the cathode and passing through the transparent indium tin oxide anode electrode. So the light coming out of this one will be measured for the to characterize the devices. So there are the different parameters to be optimized. So charge balancing charge should be injected, and the various parameters such as thickness and the work function of the electrode would be very important to make the balanced charge carriers in the organic light emitting diodes. And to give the higher device efficiency, the more number of excitons should be formed, and so the internal quantum efficiency should be 100%. So in case of organic semiconducting material, the internal quantum efficiency is achieved to be 100%, whereas still the external quantum efficiency is not achieved to the highest level. So still the work is going on to achieve the external quantum efficiency in the devices. So this is the typical devices we have made in our lab, and you can see that the injection and the transport of charges in the organic light emitting diodes. You can see that the aluminum lithium, the combination of lithium fluoride and aluminum combination, cathode will inject the electrons into the electron transporting layer and being transported and being trapped at the light emitting layer. And similarly, the high work function transparent indium tin oxide is injecting the holes into the hole transporting layer and being transported and trapped in the electron transport layer. And so in the light emitting layer, the electron hole exciton would be formed. This electrostatically interacting electron hole pair exciton will be decaying to give the light emission. The light emitted will be passing through this transparent indium tin oxide anode material. So this is the typical device we have made in our laboratory. So the organic light emitting diodes are being used in the being used for various applications. So right from the genetic displays and the roll-to-roll manufacturing, organic layers for the flexible devices, which can be made into which can be rolled into a small device structure, and whenever you need, you can stretch it out. You can see the displays. So the flexible and foldable devices can also be possible using these organic materials. So your mobile phone can be just folded into small piece and kept in your pocket. And so whenever you need to see that display, you can stretch it out and you can see your display as a mobile display. And so the light emitting screens can be made by inkjet printing onto a flexible substrates, and that can be pasted on the wall, which will your entire wall can be emitting the light to illuminate your home. So, and also this kind of LEDs can be used for the white light emitting purpose. So these are some of the applications of this organic light emitting diodes. These advanced technologies are yet to come up. So these are just a projection where the organic light emitting diode based displays and the lighting sources can be used in the future technological devices. So these are the various steps involved in the fabrication of organic light emitting diodes. So you can see that you can see that the LEDs are the LEDs are fabricated in our lab. You can see that the LEDs fabricated in our lab is glowing and it is being characterized. So for the characterization facilities, we have source meter and the spectrorhodiometer. So we have also made the device and based on this ALQ3 material, and we studied that annealing of indium tin oxide anode is improving the device efficiency. This is published in one paper published by the AIP. And our group is also working on organic solar cells. So you can see that the organic materials are being used in the solar cells. So in case of organic solar cells, there would be a donor and acceptor molecules. This when the sunlight is falling on this donor molecule will excite the electrons, and the electron hole pair, that is exciton, would be generated. And these excitons would be dissociated at the interface. You can see that the electron hole pair, that is exciton, will diffuse to the to the interface in the donor layer. So when it reaches the interface, you can see that there would be a large energy barrier for the holes and there is no energy barrier for the electrons to get dissociated. So you can see that at the interface, the exciton will get dissociated, and the electrons will be going to the cathode due to this energy. There is no energy barrier for the electron to reach out to the cathode, and similarly, the dissociated holes will move towards the anode because the holes will not find any energy barrier to reach out to the anode here, and hence, so in the organic solar cells, you can see that when the light is falling on the uh, donor through this transparent anode and the whole transporting layer, when the light is falling, the light energy is less than the light energy is greater than the optical band gap of this donor molecule. So the exciton would be generated, and the exciton generated would be diffused to a certain length. Within that exciton diffusion length, it will get dissociated, and the dissociated charges would be collected by the electrodes, which will give the electrical energy for the external usage. So this is how the organic solar cell is being working, and these are the projected application of these organic solar cells. You can see that the flexibility of organic molecules would be used in the organic solar cells to make the flexible organic solar cells to give the electric power in the remote areas, and also in the so the windows can be deposited by these organic solar cell materials. So to give the power to the household devices, and also it can be used for the various applications in the remote areas or in the highly cold place. So this wearable jacket can be made to power the power the mobiles and other electronic devices, and also to warm up the houses and other things. So these projected out application of the organic solar cells will be made true in the coming future. So this is the typical steps involved in the fabrication of organic solar cells. So we have also found out that the combination of annealing of indium tin oxide and the using of PEDOT-PSS whole transporting type organic layer onto this annealed ITO will improve the solar cell efficiency. So we have fabricated the solar cells based on the combination of indium tin oxide and PEDOT-PSS bilayer structure to improve the solar cells. So it is observed that the transparency is improved, and the band gap is slightly decreased because of this the absorption of this PEDOT-PSS interlayer, a polymer layer. This is a polymer layer. This polymer layer will improve the device efficiency. So we have made the device. This is the typical structure of the device, organic solar cell device, using this ITO PEDOT-PSS polymer bilayer. So this is the typical device characteristics, and you can see the energy level diagram of the organic solar cells. The materials used in the organic solar cells are the P3ST PCB combination for the donor and acceptor purpose, and the PEDOT-PSS layer is used for the efficient whole transporting in the organic solar cells. So we have achieved higher device efficiency of around 4.7 percentage by using this combination of annealed ITO and PEDOT-PSS layer. And this paper is published. This work is published in the Journal of Supermolecular and Microstructures. So next I would like to discuss about the UV photo detectors. So organic materials are also being used in this UV photo detectors. So UV photo detector is nothing but the similar to the solar cells, which will convert the light energy into the electrical energy, and which is sensible to the it is having the higher sensitivity when compared to the solar cells. So it is, there are two types of UV photo detectors. So one is the conventional UV photo detector and the self-powered UV photo detectors. So in case of conventional UV photo detectors, there would be external power source which will bias the photodiodes, whereas the self-powered, the energy difference will be making the voltage difference, and that voltage difference will give you the current collection of the, the uh, current collection, and so it is called as a self-powered device. So this is the typical working mechanism of these UV photo detectors. So in the, in the most widely UV photo detectors, zinc oxide would be the inorganic, zinc oxide would be combined with the different organic molecules in our studies. So this is the the typical working mechanism. So you can see that when the UV light is falling, there would be a dissociation of the oxygen adsorbed onto the surface will be taking place, and hence there would be a flow of excitons through the UV photo detector device. So these are the various applications of the UV photo detectors. So our group is working on the hybrid organic inorganic hybrid structures for the various applications. So in the organic inorganic hybrid structures, the advantages of inorganic structures, inorganic material would be combined with the advantages of the organic semiconducting materials. So you can see that in inorganic semiconductor material, there would be inorganic materials will have a thermal stability and electrical higher electrical mobility and durability, and also it is very strong because of this covalent bonding. Whereas in organic semiconductor material, the advantages are the coating of the organic material can be made in the normal ambient temperatures, and it is also exhibiting good electrical conductivity, and very importantly non-toxic, biodegradable, and mechanically flexible. So these advantages of these both the semiconductors would be made possible by making the organic inorganic hybrid structures. So these hybrid materials will give the both the advantages of organic and inorganic, and it is giving a very efficient energy transfer from organic to the inorganic. And the preparation method also, we can make it by using the spin coating method. We can make the uh, very highly transparent and crystalline thin films can be made. Hybrid thin films can be made by this spin coating solution process method. So in order to make the hybrid structure, we have chosen this zinc oxide. Zinc oxide is most widely well explored material, which is showing the n-type semiconducting nature, and it is having the wide band gap, high mobility, and cost effective, and which can be, the thin film can be made by the solution process method. And so various types of nanostructures can be formed by various process such as hydrothermal method and other solution process method. And we have chosen AlQ3, one of the most widely used electron transporting as well as electron light emitting material in the organic light emitting diodes to make the hybrid structures. So we made the hybrid structures. So this is the typical uh, process by which the hybrid is made. So we prepared the LQ3 solution and zinc oxide salt gel and combined together to give the organic inorganic LQ3 zinc oxide hybrid thin films. So the precursor solution is made to, it is slightly decreased because of this absorption of AlQ3 onto the zinc oxide nanoparticles. So we have also, the XRD studies shows that the incorporated AlQ3 molecules are not going into the zinc oxide structure, and it is getting adsorbed onto the surface of the zinc oxide nanoparticles, and hence the adsorbed nanoparticles, adsorbed AlQ3 molecules onto the nanoparticles will be acting as a light scattering center, and hence a slight decreasing of the transmittance is observed in the hybrid thin films. You can see that the band gap is slightly increased upon increasing of these LQ3 molecules, which shows that the formation of the zinc oxide nanoparticles in the hybrid thin films. So the formation of the zinc oxide nanoparticles and the absorption of AlQ3 molecules onto the zinc oxide nanoparticles will give the efficient energy transfer in the devices. So we have observed that there is a slight decrease in the particle size from the scanning electron microscopy and the TEM. We have studied the decreasing particle size, and also we studied the photoluminescence properties of these hybrid thin films. It is observed that in the hybrid thin film, upon increasing of the LQ3 content, the band edge emission of the zinc oxide is fourfold increased. So this shows that there is an energy transfer from the adsorbed LQ3 molecule to the zinc oxide, and hence the zinc oxide band edge emission is increased to the level of very high energy transfer is taking place. And you can see that the hybrid material excited at the different excitation wavelength will not show any emission from the doped or incorporated AlQ3 molecules, which confirms that the energy of adsorbed AlQ3 molecule will be transferred to the zinc oxide. So this property is being used in the photo detector applications. So this is the typical mechanism of the charge transfer from AlQ3 to the zinc oxide. So you can see that the hybrid thin film, in the hybrid thin film, the zinc oxide nanoparticle is covered by these AlQ3 molecules. So when the UV light is falling on this AlQ3 molecule, the AlQ3 is absorbing the UV energy and going to the excited state. From the excited state, the energy is being transferred to the conduction band of the zinc oxide, and through the non-radiative transition process, and the energy in the conduction band will be giving the band edge emission around 387 nanometer. So this is how the organic molecule in the hybrid thin film is observing the UV energy and transferring the energy to the inorganic semiconductor material. So the charge transfer mechanism is taking place in the hybrid structure, organic, AlQ3 zinc oxide hybrid structures. So you can see that the formation of the zinc oxide nanoparticle in the AlQ3 zinc oxide hybrid thin film is confirmed by the scanning electron microscopy, and the presence of AlQ3 is also confirmed by calculating the carbon to zinc ratio will give you the incorporation of the AlQ3 molecules in the hybrid thin films. So this is the typical device. We have typical UV photo detectors we have fabricated in our lab. You can see that the AlQ3 is incorporated to the different concentration, and then we have made the devices. This is the typical device structure. So onto the glass substrate, the hybrid thin film or the pristine for the reference is deposited by the spin coating process, over which the electrode is coated by the thermal operation process. So this is the typical energy level of the UV photo detector. This is the pristine zinc oxide based device, and this is the hybrid thin film based UV photo detector. So you can see that the dark current is very low when compared to the dark current is very low when compared to the standard devices. So here the incorporation of AlQ3 molecules slightly increase the dark current, because because of the energy transfer or the absorption of UV light will be causing these higher higher UV light. The formation of the zinc oxide nanoparticle will improve the crystalline property, and the nanoparticle will improve the slight dark current. So you can see that there is a drastic improvement in the light current upon incorporation of the AlQ3 molecules. So when the AlQ3 content is increased, you can see that the light current is also increased, and it gives the higher responsivity and the detectivity in the UV photo detectors. And the response also, you can see that upon increasing of the AlQ3 content, the response is drastically increasing when compared to the pristine zinc oxide based devices. So, and also we are working on carbon quantum dots. So carbon quantum dots are nothing but the particles consisting of the graphene oxide, and so the small particle which will have the large number of agglomeration of graphene oxide layers. So this will form the particles called the carbon quantum dots. So the carbon quantum dots are also prepared in our lab and being used in the UV photo detectors. So you can see that the advantage of carbon quantum dots, as already mentioned in the previous talk, that it will have the large number of defects and surface functional groups. So this the presence of surface functional groups and defects will give you the efficient absorption of the UV light, and being UV light to transport the energy, UV energy to the zinc oxide. So this is the typical processing of the steps involved to produce the carbon quantum dots, and the processing of the carbon dots zinc oxide based hybrid thin films by this solution process method. So we have prepared the carbon quantum dots, and we have confirmed the particle size around 2 to 3 nanometer particle size, and then we have confirmed the presence of the carbon content in the graphitic structure of the carbon quantum dots. So we have made the thin films carbon quantum dots zinc oxide based thin films, and you can see that the carbon quantum dots is showing the typical characteristics of around the absorption around 333 nanometer, and the formation of carbon quantum dots is also confirmed by the exposing the light, UV light. Under the UV light, it shows the blue light emission, which confirms the presence of the carbon quantum dots, and it is showing the typical PL characteristics, and it is showing the exciton dependent characteristics PL. And we have made the hybrid structure, and the hybrid film is giving the bandage emission around 380 nanometer, and it is also showing that the increased defect emission of the zinc oxide. So this defect emission in the zinc oxide confirms the transfer of energy from the carbon quantum dots to the zinc oxide. So you can also see that the transparency of the hybrid thin film and carbon quantum dots based zinc oxide hybrid thin film is close to above 90%, close to 100%. It is even after incorporating the carbon quantum dots, the transparency of the film is maintained to the highest level of 96%. So you can see that the carbon quantum dots zinc oxide based hybrid thin film based UV photo detectors. So you can see that the dark current of the pristine zinc oxide based device is decreased. This decreasing of this dark current is attributed to the presence of zinc oxide nanoparticles having the carbon quantum dots onto the surface. So the improved quality of the zinc oxide by forming the nanoparticles, the dark current is being reduced, and also the absorption of the carbon quantum dots onto the surface makes the surface barrier larger than the pristine one, and hence the dark current is being reduced. And when the UV light is falling on this device structure, you can see that the light current is quietly improved, and which is giving the higher device efficiency. So you can see the response, the UV response is improved when the carbon quantum dots is incorporated into the zinc oxide thin film. So the incorporation of the carbon quantum dots make the zinc oxide nanoparticles, and also it is absorbing the UV energy and transferring the energy to the zinc oxide, giving the higher UV response in the UV photo detectors. So this is the process by which we made the zinc oxide nanorods and immersed into these carbon quantum dots. Means we made the carbon quantum dots absorbed onto the prepared zinc oxide nanorods, and this nanorod NC carbon quantum dots based hybrid thin film is being used in the photo detectors. So you can see that the nanorods are grown onto the zinc oxide seed layer, and the grown nanorods are immersed in the carbon quantum dot solution, and so we observed that the immersed film, the immersed zinc oxide nanorods giving the better performance in the UV photo detectors. So this shows that the immersing time is varied for the immersion. So variation of the immersion time means the increased immersion time shows the incorporation or the absorption of the carbon quantum dots onto the zinc oxide nanorods. So this the nano rods immersed into the carbon quantum dots makes these carbon quantum dots are adsorbed zinc oxide nanorods. With this structure is being used in the UV photo detectors, and you can see that the nanorods grown on this zinc oxide seed layer is being conformed using this FESM field emission scanning electron microscope, and then the incorporation of the means the absorption of the carbon quantum dots is being confirmed by the EDAX. And you can see that even after immersion of the nanorods in the carbon quantum dot solution, you can see the transparency is still maintained to a high level, and the absorption in the UV range is being decreased. And the absorption is in the UV range is increased upon incorporation of the carbon quantum dots. So upon increased number of carbon quantum dots in the nanorod thin film, the photo detector performance is being improved, and that is being studied in the device structure. So we have observed the improved performance, improved photo response when the carbon quantum dots are being incorporated into the zinc oxide thin film, as well as absorption of the carbon quantum dots onto the zinc oxide nanorods. So we have found that the external quantum efficiency is improved when the number of carbon quantum dots absorbed onto the nanorods are, to a particular level. When the number of carbon quantum dots are increased, the external quantum efficiency of the photo detector is decreased. That shows that the concentration quenching is taking place in the photo detectors. So with this, I complete my talk, where I have discussed about the organic semiconductors and their application in the various devices, such as OLEDs, organic solar cells, and organic photo detectors. And also we made the hybrid thin films based on the zinc oxide inorganic material and carbon quantum dots and the organic material ALQ3. So these hybrid thin films are also being used in the photo detectors and to see the performance, and we have observed that the organic or carbon quantum dots based hybrid thin films are giving the better performance, and which will be used for the highly efficient OLEDs and solar cells and UV photo detectors for the cost effective and affordable commercial applications in the future. So with this, I thank the organizer for giving me this opportunity to share some of the results which we have carried out in our lab. Thank you very much.
Sir, thank you for your wonderful presentation, sir. Thank you.
So if you have any question, so
yes, sir.
Yeah, I have not discussed any of the fabrication or the synthesis process. So for those who are doing any, any related work, probably if you have any question, so I can discuss.
Yes, sir.
Thank you, sir, for your nice presentation. Definitely, it will help us to grow in our further studies. We conclude this second session. The participants may ask a question or kindly type your questions.
If the participants have any question, means you can post your question in the chat box. or else you can unmute your phone and you can ask the question.
It's time for asking questions. If anyone wants to ask question,